All right. Okay, so you might have seen in the title of the workshop this name, TCAN. So I wanted to take a few minutes on this workshop to explain to you a little bit what this is about. So first of all, let me tell you who we are. The TCAN stands for Theory and Computational Astrophysics Network. It's a collaboration that was funded 4 years ago now by NASA under this program that takes this name. And we never actually bothered to change the name of our collaboration, so we call it TCAN on BNS. And the institutions involved in this collaboration, and you see some of the people here in the pictures. The institutions are of RIT, Johns Hopkins University, Goddard Space Flight Center, now the University of Idaho, West Virginia, are the four institutions that originally wrote the proposal to start the collaboration. And we have several now collaborators that have been accrued during these 4 years from a variety of universities across the world. So we have this site called compactbinary.org, where we are bringing together the expertise and the workforce in this collaboration. So far, we have about 40 people. They're not all listed here, but the number of people who have been accruing to our collaboration has been increasing. So the people can come in different roles, whether they are involved in simulations or astrophysics, or simply contributing in any way they feel proper for this. We do have also some community goals. This is actually organizing these workshops annually. We do provide open source codes. You might have heard about this already a little bit from Zach Etienne and Josef Slochower about the tools that we provide and the data, and we also provide some data, in particular initial data, but not only initial data that we like to share with the community from our simulations. So first of all, let me tell you what is the scientific goal here that we are all after. We have many scientific goals, of course, a part of our collaboration. It was an ambitious goal to start with, but the main one is to really perform this seconds-long post-merger simulation of binary neutron stars. I don't have here to review why this is actually a very challenging problem. Just to remind everyone that these simulations being very challenging so far, do not really go down to the resolution required to resolve properly the MRI, the magnetic field growth. So we are, most of the simulation focus around 100 meters. And they do have, therefore, to start with unrealistic high magnetic fields of 10 to the 15 Gauss or so. They have limited microphysics and equational state, with some few exceptions, as we have heard in this workshop, and notable exceptions. One of these exceptions that has been standing out there for quite a bit now is this simulation done by Kiyuki in 2015, published in 2015, where he was able to resolve the post-merger for at least 17.5 meters. So we have heard from Masaru Shibata today that he's actually doing a new simulation of this type. But as we all know, this simulation took many, many months and a lot of resources to be done. As we heard also from Masaru, we need to be able to simulate roughly 1 to 10 seconds, depending on our goals. And so that beyond the merger, of course, and that at the resolution required to resolve the magnetorotational instability. Here are the different time scales that Masaru reported for the various type of physics that one wants to do. Now, as I say, this is a really challenging goal. And the way we decided in the collaboration to address it was to actually take a little bit of different route than doing the using a lot of computers, which we, by the way, we require. But we decided that the way to deal with this problem was to build an integrated set of computational tools by using different codes for different regimes, whether we were dealing with the merger, the post-merger, or the dynamics of the ejecta. So our main goals for once we chose those tools was that to make sure that we develop self-consistent physics across all the codes, and we developed a self-consistent also handoff tools to make the transition from one code to another, and that's what I'm going to be talking, and the talk after me also for Ariadna will be focusing on. So one of the other goals that we had was to produce an initial data pipeline and explore a variety of scenarios and put out there some of these initial data available for the community, which are right now available under compatbinary.org. And then, of course, using the initial data, perform accurate simulations with at least resolution of 80 meters, but beyond that, and then go and use magnetic fields that are a little bit more realistic to neutron stars. Okay, and so we would perform these long-lived post-merger simulations, reaching about 1 second or so on, and focus on a lot of the physics that people are interested in for the post-merger phase of the binary evolution. So how do we do it? We divide the problem, as I said, into different regions or regime, if you want. So there is the merger and the dynamical ejecta that happened during the merger, and then there is the formation of the black hole remnant or neutron star remnant. And here, this is characterized mostly by accretion, resolving MRI, and so also looking at jet formation. And finally, there is the jet propagation, a breakout, and the jet expansion. And for all these different three regimes, we want to use the best tools that are there and then resolve the differences that are inherent to these codes because they've been written by different collaboration, different people, and then connect them in a way that is reliable for us to explore the physics of binary neutron star mergers. Okay, so first I want to tell you a little bit about this, not much because it's been already addressed. As for the merger codes, we are using the codes that are part of the Einstein Toolkit. In particular, this is Illinois GRMHD. I believe already Zach Etienne has give you a presentation of the capability of this code. And a very similar code, Spritz, was also presented by Jay Kalinani. These are the two codes that we have been using so far for doing merger simulations. There is a new code that we are actually working on. It's called AsterX. It's a new GRMHD code that actually will be built on top of what is called now CarpetX, a new adaptive mesh refinement based on MRX that has also GPU feature, and we're very excited about this possibility. Now, there are many codes out there. We have chosen the codes that obviously the members of our collaborations are most familiar with, but these tools will take us to hopefully being able to parallelize our codes to thousands of processors. And so making these codes really part of the modern infrastructure these days. Okay, so we also have community projects. As I mentioned before, this is to provide initial data pipelines via the Lorraine framework. There is also a semi-community, in open project right now that started from Lorenzo Enoji here, a graduate student at RIT, where he started to compare some of the codes among for doing binary neutron star simulations. And we discovered that actually this is a much needed direction our field needs to take. because we are finding that there are some subtle differences, like, for example, the binary neutron star inspiring at slightly different rates and so on, that needs to be resolved. So this is fairly important. I would like this community beyond this workshop to consider joining our Slack and Compat Binary for joining also the code comparison effort. Okay, so the post-merger, will be the way we're dealing with the post-merger is to instead consider the use of spherical cylindrical coordinates. We do, in fact, use codes that are widely used in astrophysics, in particular black hole accretion, because these codes are very good for angular momentum transport. Clearly, the flows are nearly aligned with the cell boundaries. And we have heard again from TCAN about the efficient grid structure that can come with these curvilinear coordinates. The two codes that right now we're using in the collaboration, the main code I think will be described here is harm plus NUC is called, and it will be described by Ariadna, because she is actually the main developer. And she will be talking about harm NUC that is used to perform our post-merger simulations. There is a new code. This was presented by Josef Zlochover that is also built on spherical coordinates that is actually built on the ancient toolkit and inherit all the great things of the ancient toolkit, but also use a very efficient current condition that allow us to really make a breakthrough in advancing our simulations for the post-merger in an efficient way. Okay, so let me tell you now a little bit about the handoff strategy. You're seeing here a movie. Actually, if you follow a little bit the movie, you will see that there is at some point a Cartesian grid, and then you see a switch to a spherical polar grid right after the merger and the black hole formation, but you see how smooth that is being done. And if you do, I wouldn't picture here, we wouldn't picture the grid, you would not even know that there are two different codes performing this simulation. Now, this handoff procedures was developed mainly by three people, but as part of the collaboration here, Federico Lopez Armengol, Ariana Morguia-Bertiers, and Leo Bernek, as well as Zaketian and others that are part of the collaboration, worked in really designing this complex workflow that goes from the linear geometry to harm plus NUC. And it's working really fine. So we have tested this handoff for the missing link simulations of binary star mergers, and we have been able to recover all the known results for example, the disk evolutions, the binary star merger and disk evolution, and the ejecta that you can see here. We also have performed some very nice diagnostic tools about properly to investigate how properly we resolve the MRI during the post-merger evolution, which you can see here. Some of these diagnostic tools give us a really good handle that we are handling really good the resolution of the MRI during our evolution. So I want to, because my time is limited, I want to just say a few words that this was, of course, a test run, and we are now performing our first science case simulations. This is actually a simulation using the equational states that have been mentioned in this conference. These two equational states, Elastic20 and slide 4. It uses leakage, neutrino leakage, and is right now underway on the TAC supercomputer. And we're going for extremely long simulations. We are heading toward the 1 second threshold. The simulation just started. It's about, I think one of the first trial simulation went up to nearly, by now, I think 90 milliseconds. You see here just a few snapshots of the magnetic field intensity and how it grew during the simulation, for example. I think Ariana will have more time to review these results, but we see this growth, which we find very exciting. We are still analyzing our first results, and well, stay tuned for more, because I think this set of tools are really promising in allowing us to continue the binary merger evolutions for the post-merger beyond what most people do around 100 or 200 milliseconds. We want to go to roughly a second or beyond. So thank you very much, and I'll pass on the word